Let's go ahead and get started. Like I mentioned, this is kind of our really last required topic this semester. And it's one we've been sort of touching on, but not really covering in a more comprehensive manner. So parts of this may not necessarily be review, but may look kind of similar to some other ways we've been discussing malware in the context of IoT or in the context of software vulnerabilities. So there is a relation there. So it's in part kind of a categorization, kind of terminology topic, which is it is a broad category. Malware is just anything that's a malicious piece of software that can threaten our confidentiality, integrity, or availability. Where this is a little different from what you've experienced in the lab so far is we've primarily and sort of intentionally just stopped at the point of you've generated a reverse shell or you've forced a login, and we've kind of just stopped there. Under the assumption, I think the correct one, that once you've done those things, you have a lot of future things that one can do, and that's a pretty critical first step that one would want to obtain. But malware can do a lot more. So we're going to talk about what are the other things that malware can do beyond just providing access. The term, at least originally, if we think of it these ways, was originally a portmanteau of malicious software. That's all it's meant by the word malware. It says malicious intent, and it is a piece of software. So it's any program that is designed to just cause some damage to systems, to compromise the computing function of a system, or to give access to the creators of the malware by bypassing existing access controls, or just leak information. So our confidentiality, integrity, and availability. Just in terms of what is a good working definition, it's just any software that does bad stuff, where bad is the purview of the person analyzing the software. That's not really technical, but it's a fair enough working definition. Well, one thing we'll see with this general categories of malware, and here is a small sampling of the different terms one may find when looking at different pieces of malware, is it's not really a formal categorization. There's no real kind of CVE for malware. There's just different types of functionality with different names that have historically been attached to that functionality. And at the very least, it's sufficient to understand some of sort of the computing history of malware. I think that's important. And just to get a broader appreciation for the different malicious things that a piece of software can do. This is my personal kind of very brief historical timeline of malware. This would not be from the corresponding textbook. And in the beginning, there was a computer. No, we can actually go pretty far back, and I like to start with John von Neumann. Anyone heard that name before or familiar with the name? Any classes where you've heard the name before that you've taken here? Von Neumann. If someone pronounced it von Neumann, that's fine, but I'm pretty sure it's von Neumann. Where have you seen von Neumann before? Absolutely. What class did you hear about that? Oh, that's fine. Digital logic, possibly, or computer architecture, or computer organization class. You hear it similar, or you hear it somewhere else? Comments 321 would cover something like that as well. So a computer organization class or a digital logic class, and of course, if you haven't taken those classes, that's fine. That's seemingly what he's most well known for in computer engineering. This idea of sort of the stored program computer where data is data, but instructions are also data, so we can manipulate instructions in the way that we manipulate data. That seems very obvious only because that's how we've been doing computing for 80 years. But that is originally sort of a term that he popularized and was named after him. He's actually a very fascinating person. I won't open up the Wikipedia link, but you can do so while we're covering this topic. He was what was referred to as sort of a polymath. He was someone who was just extremely smart and contributed to all sorts of different fields. So von Neumann computer is a very small part of his accomplishments. He was extremely important to the Manhattan Project to the extent that I watched the Oppenheimer movie and I was very much expecting him to be a part of it, and he's not in it, and that's kind of a mistake I think they made, although it was already a very long movie. In this case, where he's relevant for the history of malware, is he kind of popularized this early idea of the concept of self-replicating automata. So that's a very fancy way to describe a program or a process or a piece of software that can sort of propagate itself, can also do so via increasing complexity over time. You've probably heard of the term cellular automata or the game of life, maybe you've written a little simulator for that. That's really sort of invented with his idea of self-replicating automata. A fascinating mathematician and engineer and someone who's worth reading up a little bit on. That's where I start the timeline. The idea that software isn't just sort of a static thing, that software itself can beget other software. These things always seem obvious in hindsight, decades later. This is just sort of my personal historical timeline. This isn't an official historical timeline. Michael Crichton's movie, they wrote the novelization for. Westworld makes an early mention of the use of the term virus to refer to self-propagating malicious software. Anyone know what else Michael Crichton's really well known for? So Westworld's pretty well known. There was a TV show that was kind of a remake of it, Jurassic Park. So now that there's like 17 Jurassic Park movies, he's unfortunately long since passed away, but he's kind of responsible for all of those. Good read. Andromeda Strain's a good read. I don't know if you have something you want to read over summer break. And then that was just the first idea of at least first sort of popularized version of the idea that a virus isn't just a biological thing, that there's also potentially a computing analogy for this biological concept of self-propagating software. This is an important one. This is Ken Thompson. You may know him from creating Unix, or whether you want to give him credit for C, very influential in the creation of the C programming language. Also, more recently, the Go programming language while at Google. Published a sort of, I would say, seminal Turing Award lecture on reflections on trusting trust. We don't assign a lot of academic papers to read in a 2000 level class, I think, appropriately. So has anyone come across this paper before? Maybe in 2300, does it bring up this topic at all, or this paper at all? Okay, and maybe like the Hack Club or other people would sometimes, have a quick little seminar on it. I don't assign academic papers. So many of them are so bad, first off. That's one of the reasons. Also, they're dense, and they do require a lot of slow, careful reading. This is a very readable paper. It's actually a lecture kind of written down in paper form. From someone who was there from the very beginning of computing here. The idea of this lecture, and he's really just talking about his history in the early days of AT&T and the Unix operating system and the C compilers, that they were, responsible for the software supply chain for the Unix system as a whole. And they talk about, just in theory, the whole role of a compiler is to determine from source code to the underlying binary. But the compiler, I think, as we know, is itself also just a piece of software. So there's this sort of concept of hierarchical or recursive trust of the software that we run. He kind of beats around the bush a little bit, at least in this version of it, but he talks about how you can modify the C compiler to support new features. They then modified the C compiler, and he does talk about it, planted a bug in the compiler to match code in the Unix login command that when compiled, when the software for the login command, that login.c or whatever it would be called, would be compiled, it would miscompile that command so that it would accept either the intended encrypted password or a particular known password. So as part of the early days of Unix, they inserted basically a backdoor or Trojan horse into the login command. And that's, early days, Wild West of computing. I think the takeaway from that lecture, and something that I think we oftentimes still forget to this day, is that unless you are responsible for the ones and zeros that are ultimately executing, there's a hierarchy to this trust of our software. The takeaway is you can't really trust any code that you didn't manually compile yourself, because in this case, the source code for the login function wasn't at all modified. All that was modified was the compiler itself. The compiler itself would look to see, am I compiling this particular function? If I am, let's insert this backdoor to it. So this understanding that trust is actually a very tricky thing when it comes to software. We recognize that today. We also tend to forget that over time. So that's 1984, that lecture, referring to a time back in the late 1960s, early 1970s. Another major milestone is the Morris worm, sort of the first major, maybe inadvertently or maybe intentionally successful network worm that used very well understood buffer overflows these days, but then was able to propagate, take down essentially the entire internet at that time. It's an interesting story also when you can look at the Wikipedia bio of Robert Tappan Morris. At one point in time, he would have been most well known as, a convicted hacker, because it was the first major computer worm. He did get convicted under that. Then he went on, after being released, to found Y Combinator. I don't know his net worth, but it's probably quite good right now. So responsible for some of the really major um, the major software companies, cloud companies, and things of that nature out there today. I don't know if that's the path you want to follow, but clearly that's a path available to you. So create new modern type of virus, go to jail, come out of jail, form some major companies, and be very successful, get elected to the National Academy of Engineering in 2019. It's a pretty major milestone in that, showing that without much additional effort, a piece of software that is not just in theory kind of replicating, but in practice with network computers becomes a very trivial thing to be sort of self-replicating here. That's 1988 as well. And then while the history of malware is still being written today, it hasn't really ended. Then you have that kind of modern era of malware, which I'll put roughly 1990s to 2000. I've mentioned this before, where it was an interesting time where it was almost a daily, certainly weekly occurrence that there was a major piece of malware that was spreading across the internet in any given period of time. And it was just an expectation that this, that, or other service is broken, or this, that, or other file is actually quite malicious. And it was just sort of that wild west of dealing with the fact that all of the programs, all the code, all the websites we were visiting were potentially a very big risk to the end user here. I picture here Bill Gates, who bears some responsibility for the state of things back in that particular decade. How do we classify malware? One way and one mechanism by which people have done so is taking these three considerations into account. First being the propagation of the malware. What is the mechanism by which it spreads and replicates? Not all malware has to necessarily spread and replicate, but the ones that have interesting impact tend to have that functionality. Separately, we then classify by the triggering mechanism. And that's something we don't touch at all upon in our lab environment, because we want to trigger things right away, right? I have this exploit. I want to actually run this exploit when I press the enter key, because we want to get done with lab. But in other scenarios, we want to have certain circumstances that would lead to the trigger. Some of these will seem sort of obvious, but we'll go through the different triggering mechanisms that we can categorize malware with. And then what is the actual thing it is doing? What is the payload of that malware? What was the intention behind the malware? It is not always so simple as saying, I want to be able to log into this machine, or I want to have a reverse shell into this machine, or I want to be able to take down this machine. What is the actual goal of that malware is another way, that payload, that we can categorize that. I briefly mentioned this already, but there are other ways of doing this classification. And I think perhaps because of just the historical evolution of the field, it's just not as formal as how we try to break down CVEs or CWEs or things of that nature. That's just one thing to keep in mind, that if you read a different classification of malware, it's not wrong. It's just different than this one. And the other thing you'll certainly see is that these are definitely not exclusive categories. You could have a particular piece of malware that has multiple triggers and multiple ways of doing propagation and multiple potential different payloads. So it's not you have to pick one payload, one trigger, and one propagation, and that makes your particular malware. It could cross several of these themes. And so it's a little fuzzy at the edges, but in general, we can take a look at a particular current or historical piece of malware and attempt to classify it in that nature. What was the goal? How did it spread? And how did it get triggered in the first place? When we talk about propagation, again, you can go back to the Michael Crichton definition of the term. It is meant to be roughly analogous to the biological domain. So you have either your parasites that are surviving inside a host or viruses that are spread outside of the host. That's why it's called that. It's meant to be like common cold, flu virus, other things. It is meant to replicate. That is what makes something a virus. So malware and virus are not synonymous. Malware, malicious software. Virus, something that is attempting to replicate, presumably also being malicious in nature. And the mechanisms by which that propagation has changed significantly over time. Go back to the mid-early 90s era of Microsoft. File attachments and email were really the number one way in which malware was being propagated at that time. Seems kind of obvious now that, yeah, you shouldn't do that. We shouldn't trust these arbitrary files, and that wasn't the case back then. You could email your friend an exe file if you wanted to, or hide it within other mechanisms there. usually, if we think of something as just a virus versus this next category, it usually requires some sort of user interaction. The user is doing something, the user is clicking something, the user is opening something. Again, I won't say this again, but these distinctions are a little fuzzy. And if someone says no, a virus doesn't require user interact, this is the historical way we've separated these two concepts. I know this is a little mesmerizing. That's supposed to be that is a virus, and that what is that thing that's chasing it? Do we know? It does. I'm rooting for it. So it's a white blood cell, yeah. And I'm very much rooting for it. It does get it eventually. It's just repeating on a loop here. So that's a virus, and our body's antivirus software at work. That's our white blood cells at work. Um, Whereas a worm, again, think back to the Morris worm concept. It's meant to be more sort of standalone malware that, at least in theory, can replicate itself after potentially an initial infection that may itself be a virus, may require some user interaction for that first infection, then would have some mechanism of just self-propagating on its own, historically via some network connectivity. So what you'll see in the source code for these things, there's some initial mechanism of infection, and then it's scan a particular range, find some particular way to look for the next target to infect after the initial one. It is a little mesmerizing. We can stare at it for a little bit while longer if you want. It's on a loop, though. Famous historical example of a worm is the blaster worm. This is August 2003, which seems like a very long time ago, but it's really not. The blaster worm exploited a buffer overflow in a remote procedure call service. Again, remote procedure call, the ability to kind of remotely call a function on a local machine. It is something of a necessary piece of functionality if you want to have networked processes and kind of scalable things. But it's something you have to very much lock down if you want to actually be able to provide that, certainly as accessible to the internet. So it was believed, and that link is there as an attempt to break down of how the blaster worm came about. Believed to have been created by reverse engineering a previous patch. So that was today's quiz question, was about that, right? Where you have patch Tuesday leading to exploit Wednesday, and that's all that was intended to convey, that sort of pithy comment of a patch is released. Depending on how synchronized the rollout of that patch is, what that patch also does is then indicate, here is something that was potentially quite vulnerable. I had to patch this software. I'm actually very clearly signaling that something was very wrong with that software, certainly if it's a security patch. That was believed to be the case for the blaster worm. The source code is available, and I have it open here. We can take a look at it here. What's interesting about it is, I think on any level, it's not a well-written piece of software. Didn't have to be, at least not then. It didn't have to be a very well-written piece of software to have a pretty big impact. And it certainly hundreds of thousands of Windows computers were taken down via that. Attempted to do a distributed denial of service on Microsoft Update, but it did it via just a static DNS lookup, and Microsoft just turned off that URL, and then that didn't work anymore. It also had things like, I just want to say I love you, Billy Gates, why do you make this possible? Stop making money and fix your software. And another impact of that was this, and not just this, but many other related worms. And I'm not exaggerating, it was a daily, certainly weekly occurrence that something took down all personal computing that week, and everyone had to kind of scramble to fix it. Really forced Microsoft to start to get more serious about security. Some of these things ultimately get sort of publicly leaked via legal discovery, and you get to see these CEO-style memos. And this is a pretty famous one of Bill Gates deciding we actually have to start thinking about security in the products that we are making the active decision to say, if the choice is between adding a new feature and fixing old security bugs, we in fact now have to fix our old security bugs first. Not to say that they don't still exist, but that did reflect kind of a change in direction for the whole organization, with probably some good outcomes from that change in direction. Source code for this original worm is available. This is the open source version of the blaster worm. Let's make this a little bit larger here. It's really bad code. Okay, it's effective. So if it works, it's not bad code in that sense. But in terms of like, your C programming assignment and you're getting a grade for how well written your code is, I would disagree that this is well written code. A function to increment the IP address to propagate. So I'm on the current IP address. I want to go to the next IP address to propagate. This is a very weird piece of code, right? This isn't decompiled. This is the provided source code for the blaster worm. What is this code doing? Yes. Infinite loop. If the value is less than or equal to 254, increase, return. Seems unnecessary to me, right? And then that's for class D. It does so for class C, then class B, then class A, and it increments this sort of public global variable. If we see how it gets called, and okay, easy for me to criticize. I guess it's my job to criticize code half the time. It calls this function, then it takes that and converts those 4 variables to a string. That's all it's doing. %i, 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 convert that to a string. And then it takes the string and converts it to an IP address again. So it's just someone just kind of, I think, probably early version of not vibe coding exactly. There's no AI bot helping drive it here, but like, let me just try a block of code from this article and a block of code that my friend has here and this other, and just trying things until something ultimately works. And the link is provided there. You can take a look at the code for it. But it's even by the standards of 90s era networking code, it's pretty bad. The rest of it is just the infection. So we've talked about how you tend to see this kind of thing in your, I'll call it old school buffer overflow exploits, because it's providing the actual shell code to do the actual exploit. This was probably copied and pasted from somewhere else, and that's all that's happening here. And then there's the part where it's attempting to, it copies that to the big buffer. And then there's a part where it's attempting to then hit Windows update over and over again. But it was doing it by just the DNS entry, and Microsoft just turned off that particular URL, and that was able to prevent that attack from causing any more damage. One way to think about that is the security posture of, state-of-the-art software in that era was so weak that someone with that level of skill set was able to cause so much damage, and was frequently occurring and reoccurring. But it was a pretty influential worm. Another way of talking about propagation is this concept of a Trojan or Trojan horse. The idea is that your malware is attempting to hide itself or masquerade as legitimate software. That's still something that occurs to some extent these days, but our channels of distributing software have changed so much that it's much more difficult to hide a Trojan into the Apple App Store than back in the era where we would download software by going to a website and downloading the software and just kind of trusting that the software was safe. This is in some sense related to our topic on social engineering, because the idea of a Trojan software is you, to some extent, have to sort of trick the user into installing it, or trick someone to providing the software in lieu of the legitimate version of software. But that's the only other takeaways. Of course, the Trojan horse in mythological terms was a real horse, but what was inside it, what was the problem? And there's the same thing with this Trojan software. You wanted to download Photoshop, you couldn't afford Photoshop. These were tough days back in the 90s. You went to a website that claimed to offer Photoshop, and it did, perhaps, and it also included some other software alongside Photoshop here. That's the idea of a Trojan piece of malware. It's propagating in lieu of, or maybe in addition to, attempting to look like a legitimate piece of software. Here's a rejected quiz question just to check our understanding, and also to reflect the fact, as I was mentioning, that these categories aren't exclusive. Something can be X and also be Y. In this case, a user clicks a link. So there's our social engineering attack potentially to download Acrobat Reader, but then after they install the program, it turns out to be a malware program that propagates itself over the network. How would you categorize this malware? A, B, C, D, E, or F? I would call it F. right? It is both a Trojan, and then after that initial Trojan, it is then also a worm, right? So that's all I meant, that the categories aren't themselves exclusive in the sense. The software could have multiple sort of malevolent intentions, and then it would fall under into multiple buckets based on that categorization. Lots of different ways then historically your malware could have propagated. I'm not going to say these are solved issues and entirely historical issues, but this is less of an issue than certainly what it was even maybe just a decade ago. The concept of a drive-by download, it's similar to a related work. The difference tends to be if something is a drive-by download, it tends to be something that potentially automatically downloads. It's probably been a while since you visited a website and attempted to install an executable as soon as you visited the website. That was a very common occurrence, depending on what one was doing on the web in the 1990s and early 2000s. The difference, again, the Trojan horse, it's tempting to masquerade as a legitimate piece of software. I'm trying to download Photoshop.exe and I'm getting something else, or something in addition to what I was expecting. A drive-by download, I'm on a particular website and something gets downloaded just via that process here. Not necessarily the same as tricking the user, or there could also be some additional software engineering. The other term one hears is this idea of a watering hole attack. This is also related to this sort of social engineering here. But if there's a website or forums or other things that a target is expected to frequent, that's what gets infected first. You do hear about watering hole attacks. When you hear about them these days, it tends to be some sort of three-letter or other government agency that's doing that. So infiltrating the quote-unquote dark web and using that to find out information about users or to infect, users' machines who are going to a particular resource. That's just another mechanism by which that propagation can happen. They're not exactly the same thing. And then there's, again, there's kind of a huge selection of potential ways here. Other ways it can happen is via this idea of malvertising, which I don't think you see very much anymore. Maybe in some places. Malware advertising is where you potentially have a legitimate online advertisement and then something happens to cause that advertisement to then be malicious in nature. That it's an advertisement that's also potentially serving malware here. That used to be very common in the earlier days of the web, that advertising itself was also kind of a Wild West scenario. Maybe some of you do sometimes still see malicious advertisements, not ones that are necessarily delivering malware, but are trying to trick you into giving credit card information or doing other things there. Nowadays, ad networks are controlled by very few select companies. So there's much more centralized control of advertising on the web these days. So you see it a little bit less. But there was certainly a time that you wouldn't know. You'd go to a website and it was fine 99 days in a row. And on the 100th day, it happened to serve some malicious software as part of the advertising. There is still the case today, this idea of clickjacking, UI redress attack, the idea being that you're kind of tricking the user into clicking a link that isn't the intended link. This example of it is how this was done in the era of Facebook malware, where it was tracking the mouse and it looked like it was, I don't know if you've used these before, the traditional like Facebook like button. That's very dated. I know no one uses that anymore, but the Facebook like button, and as part of the website, it would just hide kind of an invisible element on top of it. So you go to click the like button, you're actually clicking some invisible element leading to whatever that click was intended to go to. That's clickjacking. You're kind of hijacking a click that was intended for a legitimate reason, and you've tricked the user into clicking something malicious and instead. That still happens today, but there's various web standards that kind of limit the impact of that. Back when there was Flash and Flash-like plugins, and there was a lot of active code being run on client side to present the website, that was a more common issue back then as well. Let's talk about triggers then, and then we'll continue on this topic on Tuesday as well. In our lab, our triggers were immediate. When we press enter, we want the malware to trigger. We want the exploit to trigger. We do that just because we want to show what happens in practice. But in practice, though, in reality, I guess I should say, malware can lurk and only trigger under certain conditions. These are also two complementary concepts here because a time bomb is also a type of logic bomb. But a logic bomb, and here we're referring to sort of like the digital logic or software logic, it's a piece of malware that executes only when certain conditions are met. Anything that has an if statement to determine whether or not to trigger the malware qualifies then as a logic bomb. Some Boolean logic is being executed, and only then does the malware itself get triggered. That related concept is referred to as a time bomb, which has a time-based trigger. The infection is potentially happening at some point. The actual malicious activity waits for a certain period of time. Why would you want either a logic bomb or a time bomb in your? Assuming you're taking the perspective of a malware creator, why would you want either of these things? How about just a time bomb? Why would you want to encode a time bomb in your software? Sure, you said something, but you said it to yourself. It's definitely a route for stealthiness, right? Just harder to discover, harder to trace, harder to determine what has actually happened. And so in that sense, it makes a lot of sense to do such a thing. You have some initial infection, you sit lying in wait is what I was going for here, and the hope that at the time the actual malicious activity happens, it's maybe much more difficult to fix at that point. We could do that in the lab, but it's also really not necessary for our purposes. We want to look at the impact right away. We don't necessarily need to lie in wait. And there's actually all sorts of real world examples of time bombs, logic bombs in this malware. Intent does matter here, although you'll see some in the 1980s debates about whether a trial period on a piece of software counted as a time bomb or not. At least this is my perspective, that the intent matters. If the time bomb was malicious in nature, if it wasn't obvious up front that this software will only work for 30 days and then it will stop functioning, that's time-based logical trigger, but it's not malicious, I guess, as long as there's some consent involved with that. But it's very similar in nature to that. So here's an example. All these links are available, and I try to check them all beforehand to make sure they're all live when I put it up on Canvas. The story of the Great Polish Train Hack. So one rolling stock, one train car manufacturer had a logic bomb in their software that would determine when it was sent to be maintenance at a rival competing company. How would it do that? Well, it's not rocket science. It would do some sort of GPS, geofencing kind of trigger to determine this train car is now at this particular location, and then it would just stop working entirely when it detects that. This involved big legal fines. It's not that clear to me. I guess I really don't know all of the legal frameworks, and this is Europe, so it's maybe a different set of legal frameworks. That definitely seems very nasty to do. What particular laws it's broken, I can't quote chapter and verse on that. It seems like the kind of thing that should be illegal. To what extent it is or isn't, why would they have done that? What was their intention behind doing that? My train car goes to your company, then I shut it off. Why would it do that? Why would they do that? You could say they're evil people, but that wasn't the intent. I mean, maybe some definition of evil, malevolent, yes. So you stay in house, basically, right? So oftentimes the motive is financial, right? It's profit motive here. There's some really fun examples of them. There was a Siemens contractor who was a contractor consultant who made these relatively complicated supply chain spreadsheets for the company, and they just stopped working after a period of time. I don't recall for how long they worked. So the article, trusted to some extent, says the files worked for years, and then they started to malfunctioning around 2014, had logic bombs in them that would trigger after a certain date. Why would you want your spreadsheets that you yourself wrote to stop working after a certain date? Sure. Yeah, Carl's spreadsheet stopped working. We better call Carl. His rate's gone up. Well, what are we going to do? The spreadsheets have stopped working. That, again, also sounds very illegal. Federal court charge of intentional damage to a protected computer. That implies it's like DOD-related things. Whether or not that would be illegal if I did that here at Iowa State, hey, they're going to fire me. All my websites that I've created and whatnot and all my files are going to actually just deactivate at some period of time. I don't know how illegal that is. I guess they'd have to come after me to find out. Let's leave things here for today. I will insert no logic bombs into the lab for next week. But that is something I would say and not actually mean. Good luck in continuing the lab. I'll see everyone on Tuesday.